Hi there, Calc VC, welcome back. We're gonna have a short video here on the calculus of parametric equations, and then we'll have another video for this week that will deal with polar coordinates and specifically graphing of polar graphs. I know you've probably done it before, but we'll review some of that in the other video. So two different videos, hopefully you can break up your homework time a little bit so you don't have to sit down and watch a big half-hour long video or whatever. So let's just get right to it. As we saw before, polar or parametric equations, let's get this share going. Parametric equations are great because we can involve another variable. Sometimes time is kind of a convenient way to think of that other variable. And so that way each x and y coordinate is dependent on time. So thinking again, like I have, x is given as some function of time t, and y is given as some other function of time. So f of t and g of t. Then, as we plot the points around, we get the graph. And then, as I said before, once you have the entire graph, if you ignore the orientation of the graph, then you have what's called the plane curve. And the plane curve is basically just a graph like any other graph. It might do some weird things like loop over itself and stuff like that because we're not worried about the whole function aspect of the parametric equations. There's no vertical line test to see if this is actually a function or not. And so, we'll see some examples here in a second where there's some looping and things like that. What we want to talk about first is, kind of the first basic idea of calculus is, okay, so now we have this, this figure, whatever it looks like. And, we might have a graph that looks something like this. And we might be interested in one of the more basic ideas in calculus, which is, okay, well, let's talk about the tangent line. Wiggly tangent line there, sorry about that. And of course, we're going to want to talk about slope. Slope hasn't changed. Slope is still, oops, there you go. Slope is still dy dx. Okay, the big difference is here, now it's defined parametrically. So how do we handle that? Well, as long as the curve that we're looking at here, C, is smooth, remember we talked about smooth, just that f of t and g of t are not simultaneously zero, then the derivative can be written as dy dt over dx dt. And we're going to use that a lot. That's actually a really nice way to think about a derivative when you're given parametric equations. Of course, the derivative at x shouldn't be zero, right? Because then we're dividing by zero. Of course, if it is zero, we kind of know already, when you get an undefined slope, probably what that's going to look like. But yeah, so this is how we take a derivative when we're given our equation parametrically. I think what you'll see as we work through problem or two here is that it goes pretty much exactly the way you think it would go. Not too difficult here. Let's just take a quick example here. Example number 1, and we'll define x coordinate as the square root of t and y coordinate as 1/4 the quantity t squared minus 4. And we want to find the slope. Find the slope at 2, 3. You may notice I've defined the point in terms of x and y. There's no t right now, and so when we look at dy dx, right? The derivative of y, of course, well, is just if you take down the 1/4, right, or leave the 1/4, then you bring down 2 t to the first minus 0, of course, and then the derivative of x is going to be 1/2 t is negative 1/2. Okay, you can see what happens here. You get t to the 3/2. Okay, well, my point is given in terms of x and y. So I need to figure out, okay, what's the t value that gives me the 0.2, 3? Okay, and so, just looking at the x equation, first of all, let's grab a different color here. X is 2. Okay, so that means T is 4, right? Now, what I want to mention here is we should double check to make sure that that's the right T for the Y coordinate at the same point. There's a little step in later material that when we're thinking about the College Board exam, you want to be sure that you're actually on the curve. And so let's put in 4 squared minus 4. And let's see, that's 16 minus 4. That's 1/4 of 12. Sure enough, that's 3. So T equals 4 is the correct value. So what is dy dx? Well, it's 4 to the 3/2 power. Okay, which, again, square root of 4 cubed is going to be 8. So we know the slope is going to be 8. What if they'd ask about concavity? That's the second derivative. Okay, now let's think about that for a second. When we take a first derivative, we do dy dx. When we talk about a second derivative, we take the derivative with respect to x of dy. Oops, sorry. I meant to write dx down there. Okay. Well, in parametric equations, then that's the derivative with respect to x of dy dt over dx dt, like so. And you can see what happens there. We're going to get the derivative of dy dt over the derivative of x dt for our second derivative equation, right? And so, and that is actually coming from a little gray box on page 676. Oops. So you can follow that along there if you need to. So when I go to find the concavity of this graph, I say, okay, so what am I going to do? I'm going to take the derivative with respect to t of dy dt, which is t to the 3/2, over the derivative of x with respect to t. So that's the derivative. Why am I squishing it in there? I'm going to scroll. There we go. Okay. And so this is, of course, 3/2 t to the 1/2 over 1/2 t to the negative 1/2, which gives us 3t. So what's our concavity at the point 2, 3? Okay, remember that implies t is 4. Then the concavity, the second derivative, is 3 times 4, or 12. So we can conclude that the graph is increasing and concave upward at the point 2, 3. And so that's when you're working in parametrics, that's how you handle first, second, third derivative, very similar. It's the derivative of the second derivative with respect to x. And so obviously you would take the derivative of the second derivative with respect to time over dx dt. Follow along the same kind of idea. Okay, if the graph gets a little more complex, and so I'm going to do example 3 from the textbook. It's going to be our example number 2, but it's following the one on page 677. So let's just call it example 3 because that'll be confusing otherwise. That's what it's numbered in the book. They have this thing called a prolate cycloid, and so a prolate cycloid is a loop. I'll just sketch the graph real quickly here, but basically the one they're using, let's see, yeah, crosses at 0, 2, crosses down here a little bit, and then we don't know where it crosses out here and out here. Okay, but the graph itself comes through, creates a loop like so. So if we think about that point there on the y-axis at 0, 2, there's actually two different tangent lines for our graph. Okay, and so that's the thing that we have to be careful of when we're dealing with a parametrically defined function. We have to know, okay, so previously, there was only one value for t up here, right? That was going to give us the 0.23. But it looks to me like, depending on the orientation of this graph, which is, we'll see in a second, it's oriented this way, there's going to be an early point where for t that we get 0, 2, and then it's going to go through this loop, and then later there's going to be another point where we're going to go through that loop. And so we'll want to figure out, like, what are those values? Okay, so what do the parametric equations look like for this graph? Well, they are x equals 2t minus pi sine t, and y equals 2 minus pi cosine t. Okay, so when we'll be at x equals 0, y equals 2 is a good question. So let's think about this for a second. When is x going to be 0? 2t minus pi sine t, right? Well, that's when both these are going to be either 0 or equal to each other. Could be t equals 0. Okay. The problem with t equals 0 is would y equal 2 at that point, right? Because remember, we also have this equation right here we have to worry about. Definitely if t equals 0, x would be 0. No doubt about that. But if t is equal to 0, notice what happens to the y coordinate. You get 2 minus pi. Okay, that's the point when t is equal to 0 down here. Okay, so it's not t equals 0. So when else would 2 pi minus pi sine t equals 0? Well, check out at pi over 2 what happens. You get 2 times pi over 2, so that's pi, minus sine times pi over 2. Perfect. That would also be 0. And at pi over 2, guess what? This equation, y equals 2 minus pi cosine pi over 2. That's right, you get 2. So we know one of the points when it crosses here is at t equals pi over 2. What's another value where it would equal that? Well, if you were thinking negative pi over 2, you'd be right on the money. And if we look at when t is negative pi over 2, you can see that, oops, y is 2 minus pi cosine of negative pi over 2, which is also give us 2. So we have ourselves the points negative pi over 2 and positive pi over 2. Each one gives us the same xy coordinate, but because as you look at the orientation of the graph, you can see we go through negative pi over 2 first, then we come down and we follow the graph around, go through this point here, keep going around, and then we go to positive pi over 2 and work our way through. So obviously at negative pi over 2, we're expecting a negative slope on our tangent line, because you can see we're going to have a negative slope tangent line there. And at positive pi over 2, we're going to have a positive slope tangent line. So let's take a look and see, what does that tangent line slope look like? Well, let me grab our dy dx here, which is of course dy dt. Well, obviously dy dt, the 2 goes to 0, so we just have negative pi times the derivative cosine of t, which is negative sine of t, so we get positive pi sine t. And for the dx dt, the leading to t doesn't really go away, right? We're still going to have a 2 minus pi, and then we're going to get cosine t right here. And at pi over 2 or negative pi over 2, what's going to happen down here in the denominator is this guy is going to go to 0. So basically we're going to get pi times the sine of pi over 2 over 2. Well, that's pi over 2. And at negative pi over 2, we get, you can see negative pi over 2. So the slopes are pi over 2 and negative pi over 2. So yeah, we have two different slopes, two different tangent lines. We actually have the y-intercept for the tangent lines. So we know that the tangent lines are y equals pi over 2 x plus 2 and y equals pi over 2, sorry, negative pi over 2 x plus 2 for the two tangent lines at the point 0, 2. And that's kind of a thing that, you know, shows up mostly in parametrics because we have the ability to have these loops that go over themselves. So, all right. Now, one more interesting, or well, okay, that's a lie. Two more interesting outcomes of parametrics is, remember arc length way back when we were in Calc AB? You know, we had that arc length formula that said, okay, so if you want to find the length of an arc, you go A to B, and then you have the square root of 1 plus f prime of x whole thing squared dx. Okay, and honestly, I don't know if Mrs. Stuckey's class, if you guys got to that or not, but arc length was a little bit tricky because and all the functions had to be just designed just so that they all worked out just right. Well, with parametrics, this actually changes quite a bit because remember, that's a dy dx in there. So the integral from a to b, the square root of 1 plus dy dx. Oh boy, I wrote dx on the numerator. Dy dx squared in there. And now if y and x are defined parametrically, we can take this a step further and say, well, actually, that's the integral from a to b, square root 1 plus dy dt over dx dt quantity squared. And if you go ahead and make a common denominator in here, okay, so we're going to, oh, I forgot my dx. So we're going to multiply by dx dt over dx dt in here. So I want to multiply, I want to get a dx dt brought in here to make this a common denominator. It's got to be a dx dt squared, right? Oh, I didn't mean to do that whole thing. There we go. Like so. Times dx out here. Well, check it out. That's a to b square root dx dt squared plus dy dt squared all over square root of dx dt squared. Well, dx dt squared square rooted, that's just dx dt. So we have integral dx over dt squared plus dy over dt squared. This is then over dx dt, or this is times dt over dx, right? If this is in the denominator, we just want to, you know, divide by a fraction, multiply by its reciprocal, and look. Oh, I wrote a dt down here. Sorry guys, I meant a dx. The dx's cancel, and we get actually a really nice formula for arc length when the functions are defined parametrically. It's actually easier. It's actually easier to do these things when they're defined parametrically than they were when they were rectangular. So parametrics give us a nice way to look at arc length problems as well. And by extension, surface area problems. You know, just take your surface area and revolve it using a radius, and you can find, oh, I forgot my dt. You can find a surface area. You'll find both these on, this is on page 678 in the book. You can see a nice example there where they've done a nice arc length problem. And then for surface area, I won't go through a huge bunch of questions on it because, it's the same surface area stuff that we did before, but the surface area, you take your integral from A to B and you make it round, right? And so we know that we have a circumference, so we integrate 2 pi times a radius, okay? And the radius, depending on which way if we're revolving around the x-axis, then we need the y-coordinate times the little length of arc. Like so. And of course, y is defined parametrically. We've been saying along the line like x is f of t and y is g of t. Oops. Come on, Apple Pencil. There we go. So I can substitute the g of t in there. I can take the 2 pi out of the integral. And I just get g of t times the square root of dx dt squared plus dy dt squared dt. So the whole thing can be defined in terms of t. And of course, if we revolve around a vertical axis, then you're going to put everything's going to be done with respect to x. But the equation doesn't change for surface area because it's defined parametrically. There's no more like reorienting the equation. So this is the equation if our axis is going, if we're revolving, a curve like this, we're going around the x-axis. Okay. But if you want to go around the y-axis, take that and go around the y-axis. We want to have it go this direction. The cool thing about this is we don't have to change the equation nearly as much as we had to do before. Obviously, we have new limits. I'll call them C and D because we're going to go from, C here up to D here. But all that matters is we just change the radius function to be f of t. The arc length is still going to be dx dt squared plus dy dt squared. And that's the beauty of being able to do this parametrically. We don't have to rewrite our equations. We don't do any of that stuff because x, y are each defined independently in terms of their own equations. So, all right, guys, that's it for the calculus of parametrics. Hopefully that'll help you guys get through those homework problems there. Check out the next video for polar equations and polar coordinates, polar graphs. We won't do the calculus of polar this time around, but if you start thinking about it as just changing the parameters that we're defining things as, I think you'll see how it's going to play out with this parametric stuff. All right, guys. Thanks a lot. See you. Wow. Aside from 2 errors along the way there, that wasn't too bad. Edit those out later.